Welcome, esteemed colleague and guests, to our presentation on the design of a CMOS programmable gain amplifier, PGA, for reconfigurable system. I'm Abdul Hadi Abdul Razak, and it's my pleasure to share this work developed in collaboration with my talented co-authors. Today, we will explore the intricacy of designing an efficient and versatile PGA using CMOS technology. Okay, our presentation will cover the following section: introduction, overview of a reconfigurable system and the importance of PGAs, methodology, step-by-step process of designing and implementing the PGA, result, detailed analysis of the performance metrics and comparison, conclusion, summary of finding and their implication, future recommendation, suggestion for further improvement and research, acknowledgement, recognizing the support and the contribution to this project. Each section will be provide detailed insight into our design process, experimental setup, and the outcomes of our research. Okay, first, an introduction. A reconfigurable system allows for post-fabrication modification, making it highly versatile for various applications. Conditioning circuit for analog to digital converter ADC typically include a programmable sample and hold, HSC, a programmable anti-aliasing filter AAF, and a programmable gain amplifier PGA. These components are crucial for optimizing signal conditioning and enhancing the performance of ADCs in diverse environments. The PGAs adjust the gain, which is essential for optimizing the dynamic range of the system. A gain amplifier adjusts a ratio between the magnitude of input, output, and input signals. Different application requires varying gain ranges. For instance, 0 to 20 dB for biological signal processing, 0 to 70 dB for intermediate frequency IF application, 0 to 18 dB for low voltage application, and 49 dB for radio frequency RF application. Programmable gain amplifier PGAs are essential for optimizing the dynamic range of system, ensuring signal integrity across different operational conditions. Our methodology begins with designing the schematic of the PGA. The flowchart outlines the stage from initial design to final testing. Schematic design, creating the initial circuit diagram, simulation of the schematic design, testing and verifying the design through simulation, and then layout design, translating the schematic into a physical layout, parasitic extraction. This is PACS to extract the capacitance and parasitic of the layout design, and then we do a post-layout simulation, and lastly, testing and verification. Each step ensures that our design meets the required specification and performs reliably under various conditions. This structured approach ensures thorough development and validation of the PGA. Okay, this is the schematic design of the programmable gain amplifier. The PGA design involves a programmable gain circuit controlled by a decoder set by a 2-bit digital input 00, 01, 10, and 11. The gain is determined by using the following equation calculated in equation 1 and equation 2. This programmable gain is achieved by switching resistor in the circuit, controlling by the digital input. This equation forms the foundation for calculating and setting the desired gain level accurately. Okay, this is the layout design of the two-stage operational amplifier, or AMP. We designed the layout of the two-stage operational amplifier, a critical component of our PGA. This op-amp ensures high gain and stability, essential for accurate signal amplification, and layout design include careful consideration of parasitic elements to minimize their impact on performance. So from the figure, you can see that there's a beta multiplier voltage reference and the two-stage amplifier. Okay, the layout design of the programmable gain amplifier. This is which follows similar principle, ensuring minimal parasitic effect and optimal performance. The layout include gain control circuitry, and necessary interconnection to achieve the programmable functionality. Okay, this is the frequency response analysis of the two-stage op-amp schematic design, which reveals open loop gain with 83.99 decibel, unity gain bandwidth 746.46 kilohertz, indicating the upper limit frequency for stable operation. The phase margin 87.89 degrees, reflecting the stability of the op-amp. These metrics validate the op-amp performance and suitability for integration into the PGA. So after parasitic extraction, the frequency response of the op-amp design shows slight variation due to additional resistive and capacitive element introduced during the layout. The result demonstrates minor changes due to parasitic with an open loop gain of 83.92 decibel, gain margin of 33.95 decibel, and phase margin of 88.10 degrees. Power consumption increased slightly to 120.64 microwatt due to additional polysilicon connection. The stability and performance metrics remain within acceptable range, confirming the robustness of the design. So we're comparing the pre-layout and post-layout specification. The open loop gain, A or L, for pre-layout is 83.99 decibel versus the post-layout, which is just 83.92 decibel. The gain margin, again, for pre-layout, 32.49 decibel, with post-layout, 33.95 decibel. The phase margin, pre-layout, 87.89 degrees, for post-layout, 88.1 degrees. Power consumption for pre-layout, 113.65 microwatt versus the post-layout is around quite a little bit higher, 120.64 microwatt. Minimal differences indicate effective design practices minimizing parasitic impact. So the voltage response of the PGA schematic design was tested with a fixed input of 60 millivolt. The output voltage varies based on the 2-bit digital input, demonstrating programmability and effectiveness of the gain control mechanism. So here's when we change from this is 00, first diagram, second is 01, and then we set to 10. They change the resistor connectivity, which differentiate the gain. If you can see from the figure that we show here, and the last one is when we set to 11. So the gain is highest, very incrementally. So here's the summary. What we did is a comparison with the PGA under different input with theoretical and calculation. We compared the responses of PGA. The output remained consistent, confirming the layout design effectiveness in maintaining desired gain levels. So, for example, 00 theoretical is 20 dB. Calculation is 12 dB, 01 theoretical 13 dB, calculation 9 dB, 10 theoretical 6 dB, calculation 3.7 dB. For 11 theoretical is 0 dB, the calculation is negative 1.23 dB. The discrepancies are due to non-idealities in the circuit, which are addressed in the layout design. So this is the output voltage comparison of the PGA under different digital input confirm the design consistency. So for 00, this result So this is the post layout. Okay, so when we compare the PGA under between programmable gain amplifier pre and post layout, we set to 0, the pre layout is 2.45. The post layout is just a little bit higher, or 2.47. 01, 172 millivolt. For post layout, 173 millivolt. For 10, 92.23. For pre-layout, post-layout, 92.54. For 11, pre-layout is 52.02 millivolt. For post-layout, 52.14 millivolt. This result confirms the consistency and reliability of our PGA design. So this is the power consumption comparison for the PGA under different digital input. Shows a slight increase post layout due to additional parasitic element. For example, for 00 is the pre-layout 113 microwatt. For post layout 120 microwatt. 01, 113, similar with the 00 microwatt. And post layout is also similar with the 00 input. 120 microwatt. For 10, 11364, 12061, 11, 11365 layout, post layout 120.62. So if we calculate the average total power for pre-layout is 113.64, post layout 12061 microwatt. So the average power consumption increase from 11364 to 120 microwatt is manageable within a design constraint. The average power consumption increased slightly post layout due to additional polysilicon connection. All right, so what we can conclude, our research in the CMOS programmable gain amplifier PGA has shown promising results. Our design with a low voltage PGA using 2-bit digital signals successfully achieve variable gains with circuit design in 130 nanometer technology. The power consumption post-parasitic extraction increased slightly, attributed to more polysilicon connection in the layout. Minimal differences between pre-layout and post-layout specification underscore the design's robustness and minimal parasitic effect. Reducing polysilicon use in layout by enhancing design optimization can further improve the performance and power efficiency. By reducing the use of polysilicon and optimizing the layout design, we can further decrease power consumption. Enhancing the PGA design to achieve more optimal gain value for a wider range of application will provide a versatile and cost-effective solution for the industry. Okay, to improve our design, we have 3 suggestions for future recommendation. Reduce polysilicon usage. Minimizing the polysilicon in the layout will help reduce power consumption. Second, optimize layout design. Smaller design will lead to more efficient and cost-effective fabricated chip. And lastly, enhance PGA design, developing a more versatile PGA with a broader range of gain values will benefit various applications. Okay, so that's come to our end of our presentation. Before that, I would like to acknowledge the authors. We express our sincere gratitude to UITM RMC for the PYPB incentive and project support. A special thanks to the School of Electrical Engineering, College of Engineering, UITM for providing the necessary lab space and equipment. And lastly, thank you for your attention. We welcome any question and discussion. Your feedback and insight are greatly appreciated as we continue to advance our work in IC design and a reconfigurable system. Thank you. Assalamu alaikum.